Let's take a look at implicit differentiation. I use this to find the derivative of a function in terms of other functions. First, let's figure out how implicit differentiation is different than what we've normally been doing to take the derivative. Right now, we've been doing explicit differentiation, or just regular differentiation. So we're given a function of a variable, f of x, and we find its derivative in terms of that variable x. So an example is f of x is x to the fourth. Take the derivative and it's 4x cubed. But implicit differentiation is different. We're going to be given an expression that could have multiple functions and variables. Then we find the derivative of a particular function in terms of the functions and variables that were in the expression. So an example would be x cubed plus y cubed equals 2x times y. So y is actually a function of x, and it's being cubed right now. We're not used to that. So we would be finding the derivative of y, or dy dx, as a function of y, a function, and x, which is a variable. And this is why implicit differentiation is different. So there are two types of implicit differentiation. Now, the first one I call type 1. We're given an expression that has two variables, like x and y, and then we're asked to find a derivative of one of those variables with respect to another, like find dy over dx, or the derivative of y with respect to x. Now, the second type I call type 2. We're given an expression with two variables, like x and y, and we're asked to find a derivative of one of those variables with respect to time. So we're asked to find dy over dt, the derivative of y with respect to t. Now let's look at the steps for solving both types, and then I'll explain the justification for those steps. Let's look at type 1. So we're given an expression that involves two variables, x and y, and we're trying to find the derivative of one variable, y, with respect to the other, x. So here are the rules. We're going to have to derive both sides. Now when we derive terms that have x in it, we derive them like usual. So x cubed would become 3x squared. When we derive the terms that have y in it, we use the same rules that we use for x terms, and then we multiply by dy over dx. So just like how x cubed becomes 3x squared, the derivative of y cubed would be 3y squared times dy over dx. Now, we have to use the product rule whenever x and y are multiplied together, and the quotient rule when they divide each other. So once we derive both sides, keeping these rules in mind, we have to get all of the terms that have dy over dx together. Then we factor out dy over dx and solve for it in terms of x and y. Let's look at a quick example. So first I'm going to derive both sides. I start with the left side. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared times dy over dx. The derivative of the right side, 2xy, is going to require the product rule. So I get 2 times y plus 2x times 1 times dy over dx. Remember that the derivative of y is going to be like the derivative of x. So the derivative of x is 1, the derivative of y becomes 1, and then we have to remember to multiply by dy over dx. So now we have 3x squared plus 3y squared times dy over dx on the left side, and 2y plus 2x times dy over dx on the right side. Let's get our dy over dx terms together. So I just move them over to the left side. Then I factor out a dy over dx, and then I get that by itself, and I get dy over dx equals 2y minus 3x squared over 3y squared minus 2x. And that's going to be my answer. Now, if we look at this answer, it's pretty strange because the derivative of y is an expression that has that function y inside of it. And this is why implicit differentiation is really different than what we're used to. But if we follow those steps, we're always going to get the right answer. Now let's take a look at type 2. We're given x squared plus y squared equals 4. We want to solve for dy over dt. So the answer is going to be in terms of x and y and dx over dt. So here are the rules. Derive both sides. When we derive x terms, we derive them the same as we usually do, and then multiply by dx over dt. So the derivative of x squared would be 2x times dx over dt. Then when we derive the y terms, we treat y like you would treat x, and then multiply it by dy over dt. So the derivative of y squared would be 2y times dy over dt. Again, we're going to use the product rule whenever x and y are multiplied together, and the quotient rule whenever they divide each other. Then we're going to get all the dy over dt terms together factor out a dy over dt, and solve for it in terms of x, y, and dx over dt. Sounds like a lot of steps, but it's really not that bad. Let's take a look. So when I derive the left side, I get 2x times dx over dt plus 2y times dy over dt. And the right side is the derivative of a constant number 4, which is 0. So now I need to get my dy over dt terms all on one side. So I have 2y times dy over dt equals 0 minus 2x times dx over dt. Then I get dy over dt by itself by dividing each side by 2y. And I get dy over dt equals negative 2x times dx over dt over 2y. Now let's look at where these rules come from. When we're given a type 1 problem, we're assuming that y is a function of x. And that's because they give us an expression that has x and y in it, and we want to find dy over dx, the derivative of y with respect to x. And that means that y has to be a function of x. So if we're deriving y squared, we're really finding the derivative of f of x squared. And that means that there's an inner function, because we have the outer function is blah squared, and then the inner function is f of x. So we have to use the chain rule. We derive the outer function as if it just had x in it. So the derivative of x squared is 2x, but then we replace the x with what was originally actually inside the blah squared layer, which was f of x. So instead of getting 2x, we're going to get 2 times f of x. And then, using the chain rule, we also have to multiply by the derivative of that inner layer, f prime of x. So the full derivative is going to be 2 times f of x times f prime of x. And that's equal to 2y times dy over dx, which is what we get when we were following the rules. So the rules I listed are really just having us use the chain rule. Let's look at the rules for type 2. When we're solving a type 2 problem, we're assuming that x and y are both functions of t. So we have x of t and y of t. So if we're deriving y squared, we're finding the derivative of y of t squared. So that's a function inside of a function. The outer function is something squared, blah squared. The inner function is y of t. So we use the chain rule again. If the outer layer, blah squared, just had x inside, the derivative of x squared would be 2x. But then we replace that x with what was originally inside that layer. So instead of 2x, we're going to have 2 times y of t. And then we multiply by the derivative of the inner layer, which is y prime of t. So we multiply them together and we get 2 times y of t times y prime of t, which is 2y times dy over dt. And that's what we get if we follow the rules. So that really explains where these rules come from. If you master the rules for solving type 1 and type 2 problems, you'll find that every implicit differentiation problem is the same. You just follow the rules, factor out what you need, and solve.